October. We are hanging out. We get to hear from Carson today, so it's going to be great. Microphones in this room are still good, even though this is not the normal room that we hang out in. Although, we're not using the Pel mic today, so yeah, they're still good. So just be aware of that. If you whisper, you might get picked up and put on YouTube. So,
we're recording.
Yes.
If you want to speak, we try and include the community, get as many people up here as we possibly can. If you're interested, I think we have the next couple of talks figured out, but next year, if you want to get some experience talking, if you want to give a short talk, lightning talk, if you want some coaching on how to give a good talk, it's a great place to do it. It's a great place to build that skill. Talk to me, talk to Carson, get on Forge Slack, chat with people. You can submit to the papercall.io. We do check that. But if that's a little intimidating, come talk to us. We want to get you to speak. The jobs, hiring, I know a lot of people come to network for that. We do most of that on the Forge Slack. Join that Slack group. There's tons of great channels there. We talk about Go. We talk about data engineering, ML ops, all the different stuff you might be interested in. All of the Forge meetups that get run, I think, are listed there. So if you're interested in Rust or Zig or
We don't run Rust.
oh, we don't run Rust. Never mind. If you like Rust, get out of here. But if you like Go or any of those other languages, we run lots of fun meetups. There's lots of cool stuff going on.
I gave it up too soon. I should have given it up to y'all guys.
The Go West conference is quickly coming, October 25th. If you're interested in getting tickets, please come talk to us. I think we have some tickets that we can help get you for a reduced price, maybe as cheap as free. And there are great speaking opportunities, or great speakers that are going to be there. It's always fun. Come check it out.
Hey,
It's
Carson speaking.
Carson speaking. It's a busy month. It's always a good time, and it's here, so you don't have to travel any further than you've traveled today.
Definitely stay for the after party.
And there's a great after party.
And
Wait.
Todd's providing the alcohol.
And Todd's providing that call, which means it will be even better. Yeah, so let's turn the time over.
Gotta do it.
Carson's going to give us a great talk about maps and slices. Carson always does a great job. The developer here at Weave has done a lot of Go, has a lot of deep knowledge on Golang and all of the nuances of it. So really excited to hear from him. Turn the time over and let him chat at us. Yay.
Okay, so we actually have my screen up here, so I'll just switch real rapidly and go on this. Okay, so thank you for that introduction. Like I said, my name is Carson Anderson. Technically, I'm a principal engineer here at Weave, but I prefer the title of DevXO because I made it up, and the made-up titles are always the most meaningful. That's because I work on the developer experience team here at Weave. I don't lead it, but I consider myself like the executive officer, the second in command, the guy that makes it so. And I have done that with a lot of things here at Weave. I'm here, and this is going to be such an interesting talk to do because if you might have noticed in the presentation, or as the kind of the lead up here, we want people to come talk about the Stdlib. I think one of the really cool things about Go is how much it comes with batteries included. It comes with a lot in the standard library. Previously, we seem so arrogant because it was just last meetup that Brandon spoke, and now I'm speaking. So apparently, we just are exercising all of our privilege, just come up here and speak at our own meetups and pat ourselves on the back. Yeah. But I think there's a lot of really cool stuff in the standard, and two things that are both really new and big portions of both of these packages are like, as in brand new with the latest Go release. Our slices and maps. So we're going to spend a bunch of time talking about that and hopefully kind of inspire more people to come up here and starting next year, talk about some of the other packages because there's cool stuff embedded in all of these things that just come with a language. So we're going to follow this core loop where honestly, it's going to be a little bit dry. I'm going to try to give a lot of color commentary from my history of usage and knowing what I know about the history of Go and the way it used to be. Give you a lot of color commentary, but we're just going to go over the stuff that's available to you in these two packages. For those that haven't noticed, I'm wearing our very old school Go meetup shirt, and on the back, right, it says "Simplicity is complicated." And I wear the shirt for two reasons: one, to establish my absolute bona fides for being here, right, old school; but two, because these two packages are really great example of the idea of simplicity is complicated, because you're going to see some things in slices and maps that you look at and say, like, that is boring. That is, well, duh, that's in there. Of course, you can just do that. And I'm here from the past to tell you, no, you couldn't just do that until very recently. So a lot of this stuff is simple, but it comes from this kind of past complexity. But I kind of lied in the talk presentation or in the talk title, because I have to kind of cover the CMP package. And there's a thing in here that if you don't know about it, might be the most interesting thing you learn today. There's really only 3 things in this new CMP package. It came along when generics were introduced, and it leans heavily on generics. There's just 3 things in here. There's compare, there's less, and there's cmp.org. I honestly think the bottom one's the best, but we're going to cover that last. So, really, really simple stuff. And I bring this up because you're going to see this a lot when we do, specifically when we deal a lot with the slices packages. cmp.compare and cmp.less are just give it 2 of the same thing. It can be anything because it's built on generics. So you can use these same functions. And that also might seem stupidly simple, but until we had generics recently, you didn't have the ability to even have a package like this. But you can give it 2 ints, you can give it 2 strings, you can give it 2 floats, and it's going to do a comparison of the left and the right. And if the left is bigger, it's -1. If they're equal, it's 0, and if the right is bigger, it's +1. Right. So it's just a very generic way for you to give it 2 of the same type, and it's going to return -1, 0, or +1 based on the differences. Not that interesting, but you'll see us shunting most of the complex logic of like a lot of slice sorting off to cmp.compare, because there's already a tool built in there that knows how to say what number is bigger or what string should come after the other string. And the cmp.less equivalent is, again, not terribly interesting. It's just compare, but they coerce that into a Boolean if the first one is less than the second one. Not super fancy. It's going to be pretty dry, but this is really useful, and you'll see this. I might not even play all of these. They're all playable, but you'll see this come up a lot in the rest of the talk. This is the thing. I'm going to do it really early, and you can just leave because this is probably the coolest thing if you don't know it, that it's there. The cmp.org. This is what I would call coalesce, and in the terminology I've grabbed out of the ether in my career, I would say this is what I would call a coalesce function, but they call it OR. And it's really simple, but it's really, really nice from the perspective of a Go developer that didn't get to do this before. cmp.org takes any number of the same thing. So you can give it a bunch of strings, ints, whatever, of these low-level types, and any of what they call the comparable types. And it will return the first element from the arguments that you give it that's not the 0 value. Right? So
What if they're all 0?
if they're all 0, it returns the 0 value. So that doesn't seem like much, but if you look at this, specifically this adder line here, like this used to be 6 lines of mostly empty nothing in Go, just to say, okay, do adder. Oh, is it still empty? Okay, now do add the address flag value. Is it still empty? Okay, fall back to localhost. These one-liners are really nice, and it's a really silly thing that generics gave us, but it's really, really makes your code more readable. I don't tend to subscribe to like doing things just because they're more compact, but it definitely in these cases, it's nice to just read left to right and say, oh yeah, of course, I can see these in order and just know it returns the first non-empty. So I'll run this just so you can see. Again, the same thing, it returns. In this case, I don't have any of those other config values added, so it falls back to the default one. So that's honestly one of the coolest things. If you take nothing else away, remember that comp.org exists, and it's going to save you a lot of ugly, kind of verbose boilerplate code. Now, let's go into the slices package. So we'll cover the first half. Slices, if you look at it, is massively bigger. So it's going to take most of the talk. The maps package at the end is actually quite short. If you don't know, if you're an absolute beginner to Go, and I know a lot of people here. Is anybody here like a super beginner to Go? Can we skip this? Todd, yeah, I knew that. Okay, so if you're an absolute beginner to Go, we call them slices. In other languages, you might call them arrays or lists. But in Go, they're called. We have arrays, but we don't work with them in Go. Most of the time, we work with slices, and you could consider them Go's version of arrays. And you can do these things prior to Go 121. You could pretty much do this. You could declare slices. You could index elements from it. You could take a sub slice. So you take a slice and you take another chunk of it and reference it in a new place. Or you could add to the end. And this was it. This before slices package existed. This was really all you had. You could combine these in interesting ways, sub-slicing and append, to do most of the slice operations you might want to do, but they were always painful and slow. And I'll kind of show you what I mean by that. It's also worth pointing out that, and I bring this up, you can have, of course, I showed in previous examples, slices of basic types, but you can also have, of course, slices of structs or maps or other slices. This specific example, and I bring it up because a lot of the functions in the slices package are built to operate on slices of a complex data structure, right? You'll look at it and say, well, why do I even need this? And you'll need it because between a slice of simple values and a slice of complex values, you're going to need hooks into kind of dig into these data structures. So just remember that. Speaking of the old ways, these are some examples of the slice tricks wiki, right? Anytime you need to do pretty much, and me to this day before the slices package, if I needed to do simple things like reverse a slice or insert elements at a slice at a position, I had to go to the slice tricks wiki entry and look them up. And these are verbose. And pretty much anytime I would use them in code, I would put a comment in there saying what the thing I was doing and referencing back to slice tricks, because I, to this day, could not look at this and just tell you, oh yeah, that's inserting some elements at a position. Like, that's a lot. And it worked, and we've been using Go for years without it. Generics, this was all you have, right? Other than the append on the end, everything else was way more verbose and way more complicated. I'll even pull up the slice tricks here to show you, like, these are, I gave you some short ones on that page, like filtering, inserting at places, pushing and popping, things that you think would be easy. Filtering, they're all multi-line, very complex. It almost just feels like a spell or just an invocation. Like, you just say, oh, I don't know, there's stuff here, and the wiki told me it does what I think it does. But it wasn't readable, right? And that it was kind of a detriment to the language that you couldn't do. So you don't have to do this. I kind of actually toyed around with showing you all the slice functions and also showing the old ways, but just let's pretend the old ways don't exist. When you see some really weird slice foo, just go to the slice tricks wiki and figure out what it's doing, because we don't need this anymore. Because we have the slices package. So when generics came along, we got the comp package and we got the slices package. It actually existed for a long time under an experimental package, which you can just use broad. Go's experimental packages are experimental only in the idea that they haven't decided firmly on the interface design. They're stable and you can just use them in prod. So I've been using the slices packages for a long time before they're officially added in the mainline Stdlib. But now that they're in Stdlib, I can talk about it. And then, of course, a big chunk of what I'm going to talk about today, we have our normal slices operations, and I have a huge chunk of the slices package that works on iterators, which is the hotness that was added just barely. Yes?
I was just going to say, it's totally fine to use the experimental package in your application, but if you use it in a reusable library, people will get very annoyed at you.
Oh, that sounds right. That makes
They
sense.
break all the time
That's a good
while
one.
they're experimenting.
Yes, that makes a lot of sense. Yeah, and to that point, feel free to interrupt. Like, this is dry topic, or kind of a dry topic. I'm trying to add as much color as I can and keep it interesting. But if you have questions, like, let's discuss, like, why does this functioning even exist? Or feel free to just ask those questions as we go. So now that we know that slices exist, we know it had all this stuff. I'm going to first cover a bunch of the stuff that doesn't involve iterators, and I'll throw the iterator stuff at the end because it is kind of its own beast. There's a bunch of stuff that you can do, again, on slices of any kind. So we've got helpers for seeing if slice contains something, if you can find where a thing is at a slice, or also sort of do a slice.contains, but in a more efficient way. So I'll cover all these in detail. Tell me if I get too in detail. I won't go over the code in a fine grain, but I want to kind of talk about what they do. So really basically, slice.contains and contains func both do what you think they do. You say, here's a slice of stuff. Here's a thing I'm searching for. Is it in there? And this may not seem like nothing. Simplicity is complicated, but you used to have to write, and I've probably still got 100 little functions in all my packages because I never imported them. I just rewrote them every time for string in strings or int in ints. And I would just rewrite those functions over and over again. With generics, it rewrites them over and over again for me, right? When I go in and I say, does this slice of strings contain the string? It'll write that function out and call it for me. So way more convenient. And this is our first example of contains func. So you'll see in almost every one of these slides, there's slices.something, slices.something func. And that func part is because, well, what if I have a slice of users, right? Like, it doesn't know inherently how to compare users. What does it mean for a slice of users to contain a specific user? And so very often it says, well, give me the thing and give me a function that can look at the thing to tell me how to evaluate it. So in this case, we have a slices.contains. I've got two examples here. I won't do this after this first slide. I've got an anonymous first class function where I'm saying, here's users, and I want you to find the one where u.name is Raul. And or you could kind of break it out to this other example I have, which you'll see a lot more, where I've got named functions for readability, where I've broken it out. And in this case, I can say, well, I want to find out if the slices function contains a user named Raul. Again, just different ways of passing these functions. If you run it, that's true. All of those were true.
Is this meant to be operated on sorted slices, or is this for unsorted slices?
Contains is unsorted. Yep, the next, well, in 2 slides from now, it is sorted. But contains doesn't matter. You don't have to sort it. Next is index. Index is pretty much the same thing, so I don't cover it in detail. The only difference here is instead of just giving you a true false, whether the thing is in there, it tells you exactly at what position in the slice your thing was, or a -1 if you couldn't find it. Right, so really easy. They're pretty much wrappers of the same behavior, so I won't go over them in detail. Their func variant works the same way. You just give it a function and tell it what to look for in each element to see if it matches. So that's pretty straightforward for index and index func. This is the one that where it matters, where it sorts. So slices contains, slices index go start to finish. They go over every element till they find the thing they're looking for, right? So at very large scale slices, that could take you a long time to get down in the slice. For small stuff, it's fine, just do it. But if you've got a really large set of data and you need to find something in it, and you've sorted the slice, so that's really important for a binary search to work, but and you sorted it, it works honestly in a lot of the same ways. The func variant is different, but essentially you say, okay, here's a sorted slice of things, and it's going to cut it in half, and then cut it in half again, and basically try to find the position of the element or where it should go. So what binary search does is says, okay, I found it, and it's either it's at this position or it's not there, but it should be if you were going to insert that thing. So it actually doesn't even tell you, and it has this second Boolean to say whether or not that index is where it should go or the index is where it was. So there's these two values. And again, there's the binary search func. Yep, sorry, do you have a question?
I was just curious, do you know if the comp.compare is, if they're doing any inlining or anything like that to make things quicker, or?
No idea.
I just realized why comp.or will work with multiple comp.compares. It's pretty cool.
Yeah, I don't know about that, but yeah. So there you go. So there's your binary search and your binary search func. Again, really useful if you have large data sets. Having to pre-sort it might be in itself a problem, right? But you've got some sorted data, or you just have a really large data set that you need to look through. You've got that example. So those are all your kind of searching stuff in the slices package. We're trying to bundle it up pretty tight. Next is comparison. So we've got equals and compare, which seem very, very similar, and they kind of are. We'll go over those. So we have slices equal and equal func. These do what you might expect. Equals says, okay, well, I've got 2 slices. Are they identical, right? This is sort of a replacement, a very specific replacement for a place where in the past we might have used reflect equals. You no longer need to use reflect. You can now do the slices equals, and it will just go through and make sure the 2 slices are equal. The equal func is interesting because it allows you to compare 2 slices that are of differing types, but you can write some logic where you can compare elements to each other. Their example, and I stole this straight out of their slices documentation. A lot of this is me rewriting that, I'm going to be totally honest. Their example is this int and string. Like I'm going to compare string of 1 with an int of 1, and I know how to do that conversion. The example I thought of, and maybe this is not true, but if you have, say, 2 kinds of user structs. You've got slice of users, that's the old style. You've got the slice of users, that's the new struct. You're like, oh, I know how to compare their ID fields to see if they're the same, even though they're stored in 2 different data structures. Like there might be cases where that equals func is more practical. It just, again, gives you a chance to say, I know you don't know how to compare these 2 things, but I can do that. Next is compare. And compare is a lot like equals, except it gives you the position. So it basically tries to sort of do what comp.compare does and give you a -1, a 0, or a +1. And it basically goes through the slices until it finds 2 elements that are not equal. And then it will return whether those 2 elements were, again, like comp.compare, whether the 2 elements are from the first and the second are basically how that comp works, right? So in this case, I've got a bunch of examples here where where it does that. So I won't go over that, but again, there's some really very nitpicky things. I'm sure this is super useful. I probably use slice.equal. I don't know why you would do slice.compare. I racked my brain. I'm not sure of a practical use case. I'm sure there is one. So I'm covering it. These are the ones I think everybody's been wanting for years. If you've been a Go developer for a long time, this was the thing you wanted from generics, like things, right? We're all like, oh, everything else is okay. Maybe comp.or, min and max. Felt like big gaping holes in the Go experience where we all, again, wrote 1,000 min or is max functions everywhere. So they do what you think. I don't know what else to say here. You've got min and max, and you pass some slices of stuff, and it returns the min or the max. And again, the func variants of these things allow you to write your own custom logic. You'll keep noticing that comp.compare keeps showing up in here. 99% of the time, what you do with these functions is just throw a field in a data structure somewhere. And comp do the work of compare. So in this case, I can sort, or I can find the min of a slice of ints or a min of or max of these purchases based on their priority. So if I run that, then the mins return the mins you expect and the maxes return the max you expect. It's again, boring, like really boring. But if you've been doing Go for a long time, you're really glad these are here because you're tired of writing the same function.
The two on if the slice is empty. Panic.
I don't think it panics. That's a good question. There's a lot of little gotchas, and there's a pretty heavy documentation in all of the functions to say, like, in certain cases where everything's empty, what their behaviors are. I honestly don't remember them all, but I would encourage you to look at those because they are kind of finicky, which isn't not unique to these packages. There's a lot of Go packages that have that behavior. Strings.split has some really. Oh, it does panic? Okay. So anyway, yeah, strings.split has another case where like it's very persnickety about whether it returns a slice of one empty element or nothing. So you should check out the docs on how those work. Moving on, sorting. We got min and max, and then I probably should have covered this before the binary search because I used it in binary search, but we're getting to it here. And they do what you would expect. They either sort your slice for you and they sort them in place, or they tell you if a slice is already sorted. So sort and is sorted. I'm doing it first on a very basic slice. So I've got an unsorted slice of strings. I'm going to check to see if it's sorted, sort it, and then check again. And this isn't going to surprise anybody. I'm not breaking new ground on the slices package here. Again, really, really nice stuff that you would have to write this function. I'm sure there's a million versions. These are all just, it's all kind of representative. This whole package is sort of a victory lap for the Go team of stuff you can stop writing now. That's pretty cool. And then same thing, we have sort func and is sorted func, which are the same thing. You just can write that function to do the sorting with comp.compare. And that lets you sort slices of whatever you have. These are the fun ones. These are, again, if you remember the slice tricks from before for inserting elements out of position and how much like garbage, and on to this day, my eyes just glaze over when I see that. That's a lot. These are all like easy calls. So insert, delete, or delete func are all things that you can just do. So you can make a like strings, and you can insert at a position a number of elements, and it's as easy as a function call now. So in not earth-shattering behavior, but for what it's replacing, this is nice. Same thing with delete. You can delete elements from a specific position, or, and this is kind of weird, you can delete elements based on a function that you call. So you can say, I don't want to delete them based on position. I want you to go through this thing, and especially deleting elements from a slice and condensing that down to fit them into the remaining space is a very persnickety option or operation in Go, right? If you delete some out of the middle, then because we're not using linked lists, we're using allocated big chunks of arrays of data. This handles all that for you. So you can delete a bunch of things, basically clean elements out of a slice based on a condition and not worry about how that happens. And I'm here to tell you that is a thing in Go that used to be a whole thing. If someone asked me, well, can you delete elements from the middle of the slice? I'd go look at them and say, no, I'll just build a new slice. It's easy. And I literally do that in a lot of places still because this package just came out. Yes.
Do you know if that resizes it?
It does not, I don't believe. I was looking at the documentation. There's a few of these where it doesn't actually, it doesn't reallocate anything. It kind of moves stuff around, but it does not resize.
So that essentially turns it into an inverse filter, doesn't it?
Yes. Yep. So I can run this to see, you know, skipping a lot of these, but I put comments in the code to tell you what it's going to do. Yeah.
I just wanted to also say, this is my favorite one. Because, like, to this day, I can't remember if I'm ranging through a slice and I want to delete something, is that gonna screw something up? If I'm in an iterator loop, does that change the numbers? Like,
Yeah. And in slices, I think you can't. In maps, you can. In maps, it's canonically, it's okay to delete stuff during, but it's again, it's for sneaking. And now, spoiler alert, the maps package has a similar version of this where you can just let the package do it, and then the package lets you do it. It's got to be fun, right?
and the rest, like, sure, I can range through and find a thing, but this one is like, this just removes that overhead.
Yeah, and that's also why I'm doing the talk. That's why I want to do all the Stdlib talks, because there's stuff in here that once you know about it, it opens a world of things you can write without worrying about.
We do like nested delete funcs in a couple of places.
That's cool. Next is slice manipulation. So now we've got, again, all these things that were previously slice tricks are now function calls on slices. So I'll go over these all in detail. I'm just going to give you a preview. So grow and clip are what you expected. You have a slice, and it's to give you a little spoiler and Go slices. There's an underlying array. So you might have a slice that has 5 things in it, but Go has potentially allocated some number, some other size of like future space to you. And if you want to, in advance, take a slice. I have space for 5 things. Make space for 10 more, please. You can just grow, and it will grow the underlying capacity of that slice for you on demand. Or clip will do the inverse. It will clip. And I think it does this by allocating the slices, but it does, again, take that extra capacity away. Yeah.
So that modifies the capacity, but it doesn't touch the size.
Correct.
Do you know what happens if you clip it so that the capacity is smaller than the size? Does it trim off the final elements?
You do not get to choose the number in the clip. The clip is
I
just
see. Yeah.
so it'll just take the excess allocations away. So you'll see it here when I will run this one. This one's fun because it starts out at 5 because that's what I allocated with the literal there. Then I added 10 more, and I clipped those 10. That 10 space. Stuff you probably don't need to mess with most of the time, but if it's a thing you need, you're really glad that you have the ability to kind of munge with the underlying data structure without having to do those slice tricks or some make nonsense. Next is clone. So clone this is honestly one of my most used ones. Really nice. It does a shallow clone, right? So I say shallow because if you've got a slice of pointers or structs, whatever, it's not going to dig in and make deep copies, but it does a shallow clone. So if you've got a slice of strings, and we've all had bugs where we've done the shallow, we've done just slice 2 is colon equals slice 1, and then be surprised when you're messing with both at the same time. Slices.clone makes it super easy to just get a shallow clone, which is, again, something other languages have had for a long time, but really nice to have it in Go. It saves you a lot of boilerplate code. Concat is also really cool. If you were to try to do the concat, says, give me a bunch of slices, and I'm going to jam them all into one big slice. Previously, you would have to do this with a whole bunch of appends. So you'd have append, 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 and you'd have to manually copy those. Now it's just comma at the next slice, and it's gonna it's probably doing an append behind the scenes for you, but it's still really nice that this is real convenient. 3 slices into one big slice. So I'll run that, and you'll see all of those become one big slice. So again, simplicity. It's complicated. This is really nice when you need. Repeat and replace are also really cool. So slicer.repeat does what you think it's going to do. It takes a slice and builds a bigger one where it repeats that small one as many times as you ask. So just like strings.repeat, same idea, but with a slice. And replace is, again, it takes a slice, a starting position that's inclusive, an end position that's not. So in this case, it's going to replace 0, 1, 2 with X, Y, and Z. And there are some conditions like with the other stuff where it will panic if your slice can't fit it and that kind of stuff. But really nice to just kind of really convenient in one function call, munge with your data and swap elements out. Previously, this would be individual lines for those 3 elements to say, replace each of these with these values, less readable and less flexible. So I'll keep moving on.
You can replace a range that is not the same size as the replacement, right?
I don't think you can. I think it has to be the same size. I could be wrong on that. I feel like there was some panic about your size has to equal the same amount, but I could be wrong. Next is compact or compact func. This is cool. They in the docs call this the equivalent of the unique command on Unix. So if you've ever used that, the unique command on Unix just reduces every time there's an element that is repeated in a row, uses that to 1. So if you don't sort it, you won't get absolutely unique elements, but it will say, well, you just said A, you said A again. I'm going to squash that down to be just one instance of A in the slice. So same thing. And I put this in here to show you. This A will not get replaced, but these two will get compacted into one element. These two instances of the TAMI user will get compacted into one. This will not, because again, it's not sequential. So if you want to completely get unique, you have to sort, then compact. Which is pretty easy to do, and I have an example of that later. But it's really nice to be able to say, like, here's a bunch of stuff, squish it down to just the unique stuff. Get rid of the duplicates in a row, clean that data up for them. And if you sort it, you can really get rid of duplicates. Yes?
Is that like kind of a replace? I mean, there's not a, slice dedupe or anything. Is the idea that you compose it into a sort and a compact, and I guess you're not allocating or something?
Yeah,
Or
I
it's
think,
like using a map like you would have in the past?
yeah, I think so. I'm not sure about the actual efficiency gains compared to if I needed to get all the unique elements of a slice in the past, I would make a map of that thing to construct, right? And I just throw the keys in there and let the map dedupe. You would lose ordering then, which is the big deal, whereas compact does not lose your ordering, assuming you've sorted it, right? So I don't know about efficiencies, but it's definitely got that advantage to it. So that's all the main stuff with slices. This is stuff that was all in 121. I'm going to move on to iterators. So if you missed them, I still have thoughts about iterators. We were talking about ways they're implemented, how much good do they really do, but they're in there. So we're going to talk about and there's a lot of the slices package that works on these two iterators. So there are, and I really should have had a whole slide talking about how iterators work, to be honest, but I'm going to cover them really briefly. There are, in the past, before the iterators, before 123, there was just the range keyword. And the range keyword worked on a lot of stuff and it was really nice. There's one keyword to go over maps and to go over slices, and that's actually it. No, channels, to range over channels, map slices and channels. But now, with 123, you can implement, and the slices packages does in a lot of ways, functions that return under the hood. They're functions, but just don't worry about that. Think of them as returning iterators. And iterators are not a set of data, right? You call a function, you get a slice back, you've got all the elements done. You have to allocate the whole thing at once. You have to get them all right now. Iterators are saying, look, I don't want a whole big data set with these pre-allocated. I want you to just feed them to me as you generate them. Iterators, I think, are primarily used for cases where you're like going over a cursor from a database query. Or I was talking about, we use Firestore a lot, and I would love to see iterators be taken on in the Firestore SDK and Go, because it's a little finicky the way you do it now to read all the documents from an iterator. Yes.
They just last week in the Google APIs Go package added iterators like a bulk generate for, I think, everything.
I'm gonna go rewrite my Firestore stuff, because before iterators, it's still finicky in some cases, but it's way less finicky because now you can just range over things. Before you needed like a for loop, and it was kind of janky. But for slices concerned, there's two kinds of iterators. There's the iterator that is called sequence2, iter.sequence2. You'll see this in the function signatures. And that basically is an iterator that returns two values, right? It's a function, you call it, it gives you the position and the element. And you'll see this in a couple different places. There's also iter.sequence, which is just the values, right? So there's technically nothing in the first two in the slices packages that return iterators are slices.all, slices.values. There's nothing you can do with these that you could just do with a normal range. And if I was writing code and I just needed to range over slice, I would not call slices.all or slices.values. Why? I could just, I have it. I'm just going to iterate over it. But that's, I've got an example here to show you that that's what they do. So we've got a bunch of different ways to iterate over the contents of a slice. I'm going to keep covering iterators. We're going to go over them because they're in the package and I said I'd talk about it. But I think they're the most interesting when they're combined with other things that handle iterators. So I'm doing a lot of internal slice to slice stuff where iterators are kind of an unnecessary complexity, but I'm doing it for the example of showing you how the packages work or the functions work. But I'll have some examples at the end where we kind of plug in iterators from slices and from maps and use them together in interesting ways that you couldn't before. So I think that's where their real value is. So speaking of really cool things that used to be hard, remember one of the examples I showed you was going backwards. If you wanted to reverse a slice or iterate over it backwards, you would have to do that whole slice foo trick thing. Now you can just range over a slice backwards with the range, right? You could always do this with that C style 3 part if statement, which if you don't know, Go supports that. You can just do the normal 3-component if loop. And that's how you would have to go backwards over a slice before and Go. Now you can do something that's way more obvious to the reader. Oh, I'm ranging over a slice backwards. That's actually really native and easy to understand. And here's an example of, again, feeding iterators into iterators where we've got slices.sorted, which will return an iterator, and it also takes an iterator. Or actually, slices.sorted returns a slice. So slices.sort sorts in place, right? Here's a slice, slices.sort, you don't allocate anything, it's sorted the slice where it lives. Sorted, where it takes in an iterator, reads all of the elements, and returns the sorted result of that. So it's really easy for me to, in this case, in a one-liner, range over the sorted values of a slice. So this is something that, again, is where iterators start to be helpful, because before this would be 2 lines. I'd have to sort it and then range over it. I might still do that today, to be honest, but it's really cool that you can, in the range, just say, well, what is this doing? This ranges over a sorted values of this slice. Yes.
And that leaves unsorted untouched, right? It's not sorting the unsorted. So if you need to preserve the original order.
So that's a really good point. It does. These are iterators feeding iterators. So it would leave the original slice untouched and just return a new one that you then remove. So again, pretty cool to see. These are just letters, but it all does work. Next are sorted func and sorted stable func. So again, these are the func variants, just like before, where if you've got slices of, I didn't do structs here, but if you've got slices of structs and you need to, again, get a sorted result, or you want to sort them with a function, again, different than before, because these are not in place. So that's it's a really good point. That's a major difference from the upstream packages, that you're making new slices. You're not changing the input ones, which can really change what you're doing if you mess with your input slices. And then finally, sort stable func. So I'll run these. They're all going to print the same output of a sorted array or sorted slice. Keep on into that language. It's so hard to get away from array. And if you're like me, you're wondering, what the heck is stable sort? Maybe you're not like me. And I came up kind of with a contrived example for the example of stable sort. So most sorting algorithms, not most, there's really 2 cases. There's sorting that preserves the original order, or sorting that does not guarantee that. And so my example here is a bunch of purchases. I have a bunch of purchases that have priority, right? I have the first purchase, which is priority 3, second is priority 2, third is 1, etc. So I want to sort this, but if I've got 2 priority 1s, I want to do first come, first serve, right? It's important to me that I don't munge up like, well, I'm priority 1, and yeah, but you got sorted to the bottom of everyone else's priority 1s. Like, so this allows you to guarantee in that scenario that this really only applies, I'll run this. You can run this example all day. It kind of sorted and sorted stable return the same results because it's small slices. They're pretty much, there's no guarantee, but they tend to sort in by keeping the original order. But if you have, again, huge slice of all your orders and you want to sort them by priority, but keep first come, first serve, this would be a way that you can do that with sorted stable. So kind of cool. Again, yeah.
I think it came in like 115 or something into the sort package, where they wanted to, there was whatever new hotness sorting algorithms. And so they introduced sort stable to preserve the original behavior.
Oh, is that what's going on?
So it was like, there was never a guarantee, but people wanted the guarantee. So I think that's how the sorted got in there, and then it just, follows it along.
Now, something that the language has got to do all the time. That makes sense. I like that. I like that they're like, we're going to make a faster sorting algorithm, but we want to go back to slow one with 100% guarantee. We've got to wait.
I think it's like a 10% is what they say. Like at a big thing is the difference.
Okay. And you are giving up obviously speed, or it wouldn't be the default to go the other way. So that's kind of cool. Another one that is interesting is slices.chunk and slices.collect. So chunk takes a large slice and feeds you, again, an iterator where you're ranging over small slices off of that. So you've got all these elements, and this is going to range out over them with small slices 2 at a time. And collect basically will take all of the elements from an iterator. I'm using chunk. You can use any iterator and collect them into one big slice. So again, all of these iterator stuff really is useful when you're together. If I were to run this, you would see this. It's kind of interesting. You see me chunking that large slice into multiple small ones. You see me collecting it into a slice of slices, and or just collecting just from a normal values iterator.
Did you see any examples? Chunk seems to me like a great use case for Go routines. Did you see any use of that?
They didn't have like a
That's how we use it.
Yeah.
We have like an internal batch that just made a slice of slices, and we're switching that over to.
Okay, I was gonna say, because that's the first thing I think of when I see that is like, oh, there's workers.
Yeah, that's a really good practical use cases. I've got 1,000 of these things. Give me chunks of them in 10, and I'm going to spin off Go routines to do each chunk. That's a very good practical example.
We have like two versions. One is like, I want batches of a certain size, which is, I think what this is, right? I want 2, but then we have other cases where it's, I know I have 10 workers. I don't care how much work there is. Split it into 10 chunks. And it's just a little math on the size of it.
Yeah, that's cool.
They only have the first version, obviously. There's only the one chunk, but
Yeah, you just do the math on the size, like the,
oh yeah, you're right.
it's divided by the,
Both of those, just change the number.
Do you know what the behavior is if it can't evenly chunk? Is the last slice just shorter or whatever?
It's just shorter. Let's find out. It's editable. Yeah, it's shorter. So it will still give you partial chunks at the end. I guess we could, all these behaviors, like, we've been asking what happens. I can just do it. I don't know why. It's freaking Go present. Next is append sequence. So again, this is sort of like the iterator version of just appending, right? So you've got your slice and you've got some iterator from somewhere, potentially from the slices package from anywhere. And you're just like, I want to read elements off of this iterator and append them to a slice that I have. That's all it's doing. Again, not that interesting in these cases. You could just use normal append for like this example. But when you combine iterators from other places, you can say, yeah, just read all the rows in from the iterator and put them into my rows slice that I have. That's really the power of all of the iterator stuff, to be honest. And that's it. So that was the slices package. I did want to hop back real quick, and actually we'll go backwards and show you something that well, I'll scroll it back. That got me, and I want to kind of head it off at the pass. All right, I guess I did put the link in there. All right, we're gonna pull it up. I'm gonna pull up the documentation for the slices package because it's really off-putting when you read it.
That's probably because they don't want you to use it.
Yeah, so the function signatures is a package full of generic usage and very complex generic usage. And if part of the reason I think it's worth doing this talk is if you just saw this, I'd be afraid to use this. Like, holy cow, I'm a Go developer. I'm not used to generics. Maybe somebody else can read this, but this is freaking a lot. Let's take like compare func. This is a really long one. And I say that because I went to their examples, and if you look, they have examples for all of this. You can run them and do all that good stuff. Go look at their examples if you can't remember how they work, because the examples make it very clear very quickly, like the usage, and it becomes about 1,000 times easier to use these features when you just look at their examples. The function signatures do not help you when you get this complicated with generics. I know they're as complicated as they have to be, but I just wanted to throw that out there, both for slices and maps. When you get this much generic stuff, lean on the examples. It's not as hard as it looks. It looks more and more complicated than it is. Okay, so now we'll power through all the way back to maps. Creators, maps. Okay, so same thing with maps. Again, yeah, go ahead.
So it's, I noticed that there's no apply or like map function or like reduce in the slices. Did they give any reason for why they didn't implement those or why those aren't included, or?
I have no earthly idea.
Okay, I was just curious.
Yeah.
There's still a lot of stuff missing.
Ever encountered any code base in your lifetime where reduce was used correctly that wasn't Rust?
I mean, I've used Elixir a lot, so.
Oh, okay. My guess is that the number of bad examples of how to use reduce, the number of people who know the word reduce versus the number of people who know what the semantic usage is like the galaxy to a grain of sand.
Okay,
I would totally buy that. As like, we thought it would be too easy to misuse. We put it in.
I
I
hate
think
it.
some of those are in the experimental package and were purposefully left out of Stdlib while they were like, let's wait and see how this pans out.
I love that. I still love Go for all the things that aren't in there, right? Like I had a whole talk idea for like a series of things that Go does not give us, and why that's a good thing. So I'm totally down with not putting things in there until they're really needed.
If I had a nickel for every time I was confused by code that used reduce, thinking like, oh, this person must know what they're doing because they're using reduce. This is probably a reducer, only to find out that it was like a for each that happened to track every third element's size.
It's not worth it. It's not worth the space savings. Just write the more verbose code.
Ugh.
Okay, no, that's fine.
No, it's a good question. I wish I knew the actual answer, but I think we're right on the right track with our guesses. Next is maps. So again, really, really basic map stuff. And this was kind of it. So I make the slide to point out, this was before the maps package. This was pretty much all the language gave you. If you need to do more interesting things with maps, you had to write that code yourself, just like with slices, like even very basic things. But then we got our maps package. Same thing. It was added in 121 and expanded a bunch in 123. I do have the link here for maps. I'll go to it real quick. Just again, really off-putting if you're not really familiar with generics to look these function signatures, but they do a really great job with examples. Honestly, they're missing examples for the iterator stuff, which is kind of a shame. I don't know why they don't have iterator examples, so I wrote my own. But go look at the ones that are there and it will make you less afraid to use those functions. So there's a lot fewer of them. We're in the home stretch here. We've got clone, copy. We've got all these things to kind of manipulate map data. Clone does what slice.clone does. It makes yourself a shallow clone of a map. No big deal. Again, just saves you a little bit of time writing boilerplate. Not a deep clone, but a shallow clone of a map. Copy is more interesting. I would have chosen the word copy. It sounds way too freaking close to clone, and it seems ambiguous to me. I don't know. I'm weird. I would have chose merge. That's the term I use whenever I do this operation, because copy. I know why they use copy, because IO, some of these other things, they use copies in other places in the language. But all it does is say, here's map 1, and I want you to take all the elements from map 2 and just put them over the top, right? So if it's a new element, put it in. If you already see it, right over. That it's just doing a for loop for you, honestly, behind the scenes. But they call it copy, and that's all it does is take map A and merge into it map B with override. So think of it as merge. That I don't know why they chose copy. Next is delete. Again, this is another thing. If you're not sure, there's not a straight up delete, because you just use the delete keyword still. There's no maps.delete because the delete keyword exists and it does that thing. But there is delete func. So if you're saying I have a map and I want to go through this map and remove from it all of the elements that match this condition, this can now be done with a one-liner instead of you having to loop over and call delete yourself. I actually looked it up. Interestingly, with slices you can't delete while iterating. With maps you can. It's fine. And there's places in the Stdlib where they range over a map and do delete on keys, and that was safe in maps. But now you have these helper packages for deletion. It's just way better to use those, because the next person looking at your code won't wonder, is it safe to delete the map while you're iterating? Because you aren't doing that, at least not directly here. You've got something wrapping that, making it more legitimate that, yes, it's fine that I'm deleting a map, elements from a map based on some conditions. So we have, again, equal and equal func, a lot like slices. This lets you, just like before, stuff we could already kind of do with reflect.deepEqual, but people have problems with using reflected in a lot of places. So now you have map helpers to say, are these two maps identical? Iterate over the key value pairs, make sure everything in one exists in the other and has the same values. And the same thing works with equal func. I will point out what's interesting about equal func is that it doesn't take a key. You'll notice equal func says, okay, give me map 1, give me the other, and give me a function, and have that function compare the values. So in this case, and it can actually compare different types. That's why I've got 2 examples here. Is you could have a map that is, the keys have to be the same type, but you can have a map where you have string keys to ints or string keys to strings, and you can give it a function and compare those 2 types. But you never compare the keys, and that's because map keys with the equal func are always compared with double equal, right? They don't make you do that. They say the only thing you can have be a key in Go are directly comparable types. So we don't need you to do the work that to disambiguate a thing that can't be ambiguous. I'll also point out that that's kind of cool. If you're new to Go, you can have any comparable type as a key in Go, including structs. Not pointer structs, but like hard structs, as long as all elements in the struct are directly comparable. So Go keys in maps can actually be really cool, because you can get away from using multi-depth like maps and just compare, like I want to find all the place where the user's first name is this and last name is that by making a map key struct. Again, you still, even in these complex equals comparisons, you don't have to do that because Go knows how to compare map keys. So, and that's super interesting, but stuff is really nice to have when you need it. Now we get to the iterators part, which is the last part of the map stuff, and we'll move on to kind of some use cases of combining them. So just like with slices and 123 came out and we had all these new fancy iterator helpers in the maps package. So we have .all, .insert, and .collect, which I've kind of just put into one big slide here. .all does what you might think. You can range over it. Again, not super useful. You can't just range over the map. You don't need .all. But feeding these two iterators to other things that take iterators where the value comes in. Insert does what you might expect. You can insert into a map the results from an iterator. So that's why I'm calling maps.all in here. I've got a map. Here's an iterator that provides you keys and value pairs. Insert those in. So again, maps.insert is really for chaining from other iterators. And then we have maps.collect, which again just takes that iterator and collects it into a map. Not super interesting when they're used on their own because you could just do this with normal Go in a much less convoluted way. But when you start combining them, they become very, very useful. So again, you could say, here's an iterator that's reading in rows and their IDs. And that's from some SQL library that I have. And I'm going to just collect all that into a map of users by just reading from the rows iterator. And I don't have to do all that work myself. I just have my rows iterator and I do maps.collect and I collect them all. And you're done. And so that value is really where all these packages shine. Next are some really cool ones that, again, you could do with normal ranges and they're mostly useful. And I'll show you an example of combining them, but you can get iterators over key value pairs, just the keys or just the values. Again, stuff in normal Go, we would just underscore the things we don't need during normal iteration. This might be a little bit more efficient. I don't actually know the work behind the scenes to make this. So it may be more efficient to, instead of throwing away the values every time we iterate, just iterate over the keys direct. It does make for, in cases like this, honestly does make for more readability. So I wouldn't be completely opposed to it, but I'd probably still just use this and replace the things I don't need with underscores. But they're in there and they do work the way they sound like they work. So we'll move on to the next one here. So the last little bit here where we're talking about combining those, I gave you just a really few brief examples of iterators. So here's some stuff that would have been definitely not fit on one page before these packages and before iterators. And that is, I've got a map of strings to ints, and I would like a slice of all the keys and a slice of all the values. In previous Go, this would have been 4 or 5 lines for each of those slices. Now I can take maps.keys, which returns an iterator that just returns values. It's an iter1, and collect that with slice.collect into a new slice. And so it's one liner to just read all the things from one iterator. Again, imagine your slices.collect is reading from your SQL query or from a Firestore watch or something else where you have some iterator that's working on, it could be any data set. I'm using maps here, but I think the power of iterators is combining them from as like a low level interface to all sorts of types that might feed you data progressively. But pretty cool to be able to do this and go in 2 lines, things that were previously a lot of boilerplate. And in case you want to see what this looks like, it looks like a lot, but you can write your own iterators. And I'll cover this a lot more at my Go West talk where I'm talking about first class functions, because iterators are just a highly specific Go use case for very specialized first class functions, but that's all they are. So in this example, I've got a user that's got name, age, and roles. And I have a roles method on the user that returns iter sequence. So if you don't remember, iter sequence says I'm just going to give you values. I'm not going to give you positions. I could return either of those here. And all you really do here is you return a function that takes a function and loop over your data. And anytime you have a new element, you're going to yield that element. And if the yield says false, then you're done. Like, it's kind of a lot to grok here, but essentially you plug in this section your for loop. And this could be iterating over data coming in from some network stream. It could be anything here. And the user experience is just, I don't know, I'm reading from the iterator. And anything that takes this iter.sequence will just read that in and work. So I could combine this with my maps and slices. I think I do in the next here. So here's an example where I do that. So I've got users from that previous thing. Yes.
superior yield not highlighted because this is all syntax highlighting?
Yeah, I think so.
Okay,
Yeah. Whatever I've got plugged in doesn't know about yield yet.
okay. Thank you.
So I've got a bunch of users. They've got a series of roles here, and I just like to build a slice of all the roles that all my users have, right? So I'm going to use a couple different iterators here. I'm going to take this all roles, and I'm going to use slices out of append sequence, which again was the thing in the past. We would have had to build a slice and append two slices together. But now this is a longer way to do that, admittedly, but I can say it's go over all my users and append onto the all roles everything that you read from the iterator from the users dot roles call, right? So this could be in anything you need, not just reading from data that's already in memory. And so this will build me one big slice. And then as an example of chaining things, and this is where I think readability comes into place with iterators, right? I've got this big list of all the roles my users have, and it's not deduplicated and it's not in any order. So now I can compact the sorted values of all my roles. And that's readability in your code where iterators chain in this way that like, I know exactly what this line of code is doing because I just read it like a sentence. And that was something that would be a bunch of lines that would not be nearly this readable before iterators. So hopefully I can kind of start to see the value of that chain really building things that are really useful. So if I run that, I get the results you might expect. And that's it. So if you're curious about the slides, everything I ever do is posted on GitHub. So you can pull this down, run it, and play with it yourself. And yeah, thanks again. Right. Hopefully still, if nothing else, just to open your eyes to like how much you don't have to write anymore. Like it's a talk about stop writing code. Well, not writing code. Stop writing so much code. Stop writing the code you've already written 1,000 times.
So I thought part of the reason that they didn't provide these, well, like trivial copy paste, a little copying is better than a little dependency, but also the philosophy of a package is that a package should focus around the business objective and not be according to a taxonomy, like taxonomy bad, business objective good. This goes in stark contrast to that because it is 100% taxonomy with no clear business objective. So do you know how they reconcile that difference in philosophy? Is it like tree shaking away all the extra bits of the dependency you don't need? Or they just say, well, if you're that kind of person, you just get all of it compiled into your program? Or
I don't know. I honestly think they had to once generics were introduced. I think you had to have a, like what I said this when generics came out. I think here are generics, and I said, cool, I'm probably not going to use 99% of them, but I'm really excited for a collection package. And this is just two separate pieces of a collections package, right? And I think, honestly, because some of the stuff like is just markedly better that you might break the rules to say, yes, we're breaking the rules on slices, but look, we don't need this wiki anymore to do these things.
no, I agree. I think it's really good. And I think it's also really good because it's nice to not have dependency cruft, because the problem is when you don't provide the slice methods in the language,
Right there.
then and you get the black hole dependency problem. So I'm glad that they did it. I think it's perfectly reasonable. It's just kind of, it's weird to me that for so long, because they've always had generics.
It's only for append and not for us. They had generics for them, not for us.
Yeah, and so it's just kind of weird to me because it seems like, well, we should have always had these. I respected the decision, but I just thought it was kind of odd. I'm glad to see it. And thank you for the presentation.
Yep. So if I can sit up here for an hour and talk about slices and maps, anybody can come and talk. Like, there's a lot more interesting. I left all the really fun stuff in the Stdlib to other people, to be honest. Like there's really cool stuff in there. So if you have, and this is something hopefully everyone sees that they can do, right? Go read the documentation, become familiar with the package, come up here and just tell us, go through the functions. I didn't have to do anything fancy here, just kind of digested the purpose of these things and showed how you would use them. So there's cool stuff in Stdlib. Sorry.
So one thing that occurred to me, looking at the comp.org, is that you can pass to it the result of several comp.compares. And that basically makes it if you use that for like a sorting, you can say sort first by this, then by this, then by this. Because if the first one is less than or greater than, then it's going to go after or before. But if they're equal, then it'd have to sort by the next thing. So, that was kind of a cool, it helps me understand the reason for that name a little bit better. Instead of calling it like a coalesce. The other thing is that you actually can use pointers in map keys, but don't.
Okay.
The way they get stored. So I've got a Go playground right here where you can actually use nil as a map key if the key is pointer to string.
Okay.
And but yeah, don't.
I think there's a similar gotcha. I was looking at this for functions. And
Very pointers at that
yeah,
one.
which is the same thing. And they're like,
There's memory addresses, right?
and so they don't do that. Don't. In fact,
There's a new unique package in 123. Kind of with that. You basically register kind of your pointer and then it
Exactly for the,
uniques across the actual value.
that's cool. Well, someone else will have to come talk about the unique package then. Yeah, I can see how that.
I don't think that would fill a floor.
No, but you can
know what it's for.
So if you have smaller packages, do what I did. Take 2 or 3 smaller ones, come talk about them. Doesn't have to be the flower. Our goal is we've got a big list on the Slack channel. We're checking off packages as we talk about them. Because again, there's just to be self-serving as somebody that also hosts this meetup. The presenter, see if it loads. Okay. Like there's neat stuff that just comes with the language. Like EXP bars is built-in metric system in Go. I don't know if you had that. I think Derek talked about it in the past. Like if you don't know that, you don't need Prometheus. Like there's this EXP bars thing that
well, then Prometheus will pull right from extrovert.
yeah. So there's that. There's Brandon's already talked about image handling. There's stuff with MIME types. There's a whole plugin system. I don't know a lot of people that use it, but there's an entire plugin system for Go. We plug in different binaries together. So there's a lot to cover.
Bumped in error would probably be really easy packages if somebody was looking for like an intro package. And those, I think both of those are still up for grabs, right?
Self grabs, sync and sync atomic. If you haven't, there's some really cool stuff for. There are cases when you want to use a lock end of map, but it's pretty error prone. And there are a lot of cases where it's actually better to use like sync.atomic has its own, and I've been using it quite a bit lately. Its own map types. Where is that?
Yeah, I'm pretty sure they used this in the image package if you were here last month.
Yeah. So there's really cool stuff in here. Here's that unique package that we were talking about. So again, this is super small, but you could combine this 2 or 3 other things, try to come up with a theme. So come talk to us if there's stuff in here that you're familiar with. I contend that every package in here has something interesting that even the most seasoned Go person hasn't heard of, if nothing else, because there's so much new stuff. So feel free to come talk to us about covering more of this, because I just talked for an hour about maps and slices.
And it was great.
Thank you. So, all right. So we'll call that